Consider the convex region C in R4 defined by x1 plus x2 plus x3 is less than or equal to 6, x2 plus x3 plus x4 is greater than or equal to 2, and x1, x2, x3 and x4 are greater than or equal to 0. Use slack variables to find the vertices of C. It says to use slack variables, and slack variables are designed to turn inequalities into equations. So let me write down my two inequalities. x1 plus x2 plus x3 is less than or equal to 6, and x2 plus x3 plus x4 is greater than or equal to 2. So what I need to do is add a slack variable to each of these inequalities to turn it into an equation. Now slack variables will only work on inequalities that have a less than or equal to sign. So this one's fine, but this one's not. So what I need to do is multiply this whole inequality by -1 to get the inequality sign to point the other way. So that would be minus x2 minus x3 minus x4 is less than or equal to -2. And now I can add my slack variables. Add slack variables S1 and S2 greater than or equal to 0, so that x1 plus x2 plus x3 plus S1 is equal to 6, and x minus x2 minus x3 minus x4 plus S2 is equal to -2. So I have my inequalities now as equations. How does this help us? Well, it helps us for a lot of reasons, and the first reason is to do with the slack variables. Let's have a look at our original inequalities. I've got 1 here, and 4 here. So that's 6 inequalities in total. And those inequalities define the edges of my convex region. One side of that edge is where it's less than or equal to the number, and the other side is where it's greater than or equal to. And putting them all together will define my convex region, and the vertices will be the places where various of those edges meet. So because I'm in R4, I'll need 4 of the various edges to meet to make a point. So my vertices will be the places where 4 edges meet. Well, how do I tell if a point is on the edge? Well, for these 4 here, I would tell if x1, x2, x3 or x4 were equal to 0. And for this one here, I would tell if it was equal to 2. And for this one here, I would tell if it was equal to 6. But let's have a look down at my equations. If S1 here is equal to 0, then look, x1 plus x2 plus x3 is actually equal to 6. And if S2 is 0, then minus x2 minus x3 minus x4 is equal to -2. So I actually get x2 plus x3 plus x4 is equal to 2. So if my slack variables are 0, that means I'm on either this edge or this edge. So that means that all of my 6 variables, the x's and the s's, if any 4 of them are 0, I'll be on 4 of the edges, and therefore I'll be at a vertex. But not quite, because not all of the places where 4 of the edges meet will actually be a vertex. Some of those will meet outside the set, so I need to find the ones that are inside the set, and the slack variables are useful for that as well. Because I know my slack variables have to be positive to be inside the set, that means that if any of the slack variables are negative, and also because of these, if any of the x's are negative, then that point's actually outside the set. So what I need to do is find places where 4 of the variables are 0, because that's places where 4 of the edges meet, and then check to see if the other variables are all positive, and if they are, then it'll be a vertex. The places where 4 of the variables are 0 are called basic solutions, and the places where 4 of the variables are 0 and the other ones are positive are called feasible solutions, and the feasible ones correspond to vertices. So what I need to do now, therefore, is to find out what happens when any 4 of my variables are 0 and what that means about the other variables. So let's just watch what happens here. If all of these variables are 0, I get x1 is 6 and s2 is -2. And I could do that by actually looking at the matrix as well. Let's look at the matrix. So let's see. 1, 1, 1, 0, 1, 0, 6. And 0, minus 1, minus 1, minus 1, 0, 1, minus 2. That's what my matrix looks like. And if I do the same thing I did before and cross out all the middle variables, you can see that the reason I know that x1 is 6 and s2 is minus 2 is because I have a little identity matrix just here. So, instead of thinking about making some of my variables equal to 0, instead I could think about making some of my columns into an identity matrix. And that is much easier because that's just Gauss-Jordan elimination. So let's actually do that now. It's going to be easier if I put all of this on a new page, so let me do that. What I've done is I've put the names of the variables along the top so that I can keep track, and I've put the matrix that we had before underneath. My aim now is to do Gauss-Jordan elimination, so row operations, to get little identity matrices everywhere. I need as many pairs of variables as I can to have an identity matrix in their columns so that I can read off the solutions for those variables, and all the rest of the variables will be 0. And that will give me all my basic solutions, and from there I can find the vertices. So I'm going to need to pick 2 variables out of 6 to put those identity matrices in, and that's quite a lot of combinations. So I think what I'll do is I'll make a table of all the combinations I need to do so that I don't do any of them twice, and so that I make sure I cover them all. And to do that I'll need to start a new page. I have 6 variables: x1, x2, x3, x4, s1 and s2, and I can put them all in a table like this. And then my options are x1, x2, x1 and x3, x1 and x4, x1 and s1, x1 and s2, x2 and x3, x2 and x4, x2 and s1, x2 and s2, x3 and x4, x3 and s1, x3 and s2, x4 and s1, x4 and s2, s1 and s2. And I think that's all of them. So let me just check. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 rows. And the number of ways to choose 2 things out of 6 is 6 choose 2, which is equal to 1 times 2 on the bottom, 6 times 5 on the top, which is 15. And that's the number of rows I've got. So yes, I have got all the options, so let me rub out the rest of the rows. So now I just need to go back and do my row operations. Before, I had x1 and s2, and all the rest of them could be 0. So to read off from here, I can get x1 is equal to 6 and s2 is equal to minus 2. So going back to my table, x1 is equal to 6 and s2 is equal to minus 2, and all the rest are 0. And what else can I get from my matrix? Well, there's another little identity matrix just here, S1 and S2. So S1 is equal to 6 and S2 is equal to minus 2. S1 is equal to 6, S2 is equal to minus 2, and all the rest are 0. Let's go back to my row reduction. Well, I don't think I can get any more matrices out of that one right there without doing any row operations. But I think I can get another one quite simply, because here that's almost the second column of the identity. So if I multiply that bottom row by minus 1, I'll get the second column of the identity there, and then maybe this column here and that column will make an identity matrix. So let's do that. Haven't changed row 1. And multiply row 2 by -1. So 0, 1, 1, 1, 0, -1, 2. And let's see what we've got now. Now we've got 1, 0 here, first column of the identity, and second column of the identity here. So x1 is 6 and x4 is 2. x1 is equal to 6 and x4 is equal to 2, and all the rest are 0. Can we get anything else out of this? I think we can. Look at these two. Together they make an identity matrix. They're the wrong way around, but that doesn't really matter because I can still read off from this that S1 is 6 and X4 is 2. S1 is equal to 6 and X4 is equal to 2, and all the rest are 0. I think that's all the ones I can get now. What else can I do? Well, I didn't do x1 and x2 yet. And that's not hard to achieve because I just want a 0 in this position, which I could get by doing row 1 take row 2. So I haven't changed row 2. And row 1 take row 2. 1 minus 0 is 1, 1 minus 1 is 0, 1 minus 1 is 0, 0 minus 1 is minus 1, 1 minus 0 is 1, 0 minus minus 1 is 1, 6 minus 2 is 4. And now I've got a little identity matrix here. So I can read off from this that x1 is 4 and x2 is 2. x1 is 4 and x2 is 2, and all the rest are 0. And look, there's another one. These two. So that's x1 is 4 and x3 is 2. x1 is 4 and x3 is 2, and all the rest are 0. Are there any more? Well, this one and this one together make an identity matrix. That's the wrong way around, but that's okay. So this would tell me that S1 is 4 and X3 is 2. S1 is 4 and X3 is 2, and all the rest are 0. And I reckon I can find one more. If I move this here, that's another identity that's the wrong way around, and I get S1 is 4 and X2 is 2. S1 is 4 and X2 is 2, and all the rest are 0. And I think that's all the ones I can get from that row of my matrix. Well, now I reckon I'll go back and have a look at my list and see if there's any I'm missing. Well, the first one that's missing is x1 and s1. So let's go back and have a look at x1 and s1 in my row reduction. x1 and s1. Well, if you look at that, those two columns are the same, so there's no way I'm going to be able to do row operations to get an identity matrix there, because that matrix isn't invertible. So it's not actually possible to get x1 and s1, so I'll write that information back on my table. x1 and s1 aren't possible, so I think I'll just cross them out. The next one in the table is x2 and x3. Let's go back and have a look at x2 and x3. x2 and x3, those two columns are the same again. So this one's not possible either. x2 and x3 aren't possible, so I'll cross them out. The next one on the table is x2 and x4, so let's go back and have a look at those. x2 and x4. That looks like one that might work. What do I need to do to achieve an identity matrix there? Well, I'd need to put a 1 in this spot and a 0 here. Oh, just a second. It'd be much easier to get a 1 in this spot and a 0 here, so perhaps I'll focus on x1 and s2 first. That is these two. So if I do row 2 plus row 1, that'll do what I want. 1, 0, 0, minus 1, 1, 1, 4. 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 0 is 1, 1 plus minus 1 is 0, 0 plus 1 is 1, minus 1 plus 1 is 0, 2 plus 4 is 6. So now I've got a piece of the identity here. x2 is 6 and s2 is 4. So I didn't do this one after all. Instead I did x2 and s2 there. x2 is 6 and s2 is 4, and all the rest are 0. What else can we get from this one? Well, there's another column of an identity here, so I can get x3 is 6 and s2 is 4. x3 is 6 and s2 is 4. And all the rest are 0. And can I get any more from there? No, I can't. So what's left in my table? The next row left in my table is x2 and x4. So let's go back and have a look at them again. x2 and x4, well, that's easy to turn into an identity. I just have to multiply row 1 by minus 1. So let's do that. Haven't changed row 2. Multiply row 1 by minus 1. So what have we got? We've got an identity matrix just here now. It's the wrong way around, but that's okay. So I can read off here that x4 is minus 4 and x3 is 6. We didn't do x2 and x4, instead we did x3 and x4. x4 was minus 4. And x3 was 6. And all the rest are 0. I can use these two as well. So from here, x2 is 6 and x4 is minus 4. x2 is 6 and x4 is minus 4, and all the rest are 0. Now there's only one row left in my table, and it's x4 and s2. Let's go back and have a look at those. x4 and s2, those two columns are multiples of each other. So again, I'm not going to be able to produce an identity matrix there. So that last one is not possible. It's not possible, so I'll cross it out. So now I've finally found all the basic solutions, and that's what all of these are called. I just need to pick out the ones that are feasible, and that will tell me what the vertices are. Before I do that, let me move my table down so I can say that these are the basic solutions for whoever reads this later. Basic solutions are given below. So let me pick out the feasible solutions. The feasible solutions will be the ones where all of my variables, including the slack variables, are positive. So I can see 3 feasible solutions here. This one here is not feasible because I've got a -2 here. This one here is not feasible because I've got a -4, but both of these are feasible. The next one's not feasible because it's got a -4, and all 3 of these are feasible, and this last one's not feasible because it's got a -2. So I've got in total 1, 2, 3, 4, 5, 6, 7, 8 feasible solutions. What I'll do is I'll just put a dot next to them so that the reader can figure out what they are without all these boxes lying on top of them. So this one, this one, this one, this one, and this one, this one, this one, and this one are all feasible. So I can say this indicates a feasible solution. Now the feasible solutions represent the vertices of my set, and the vertices are points in R4, so I don't need my slack variables to write down where the vertex is. They just tell me whether it's on the right side of a couple of the edges of my set. All I need is this bit of the table here. So reading off all of my feasible solutions, I'm able to get the vertices, which I'll write on the next page. The vertices of CR 4, 2, 0, 0, 4, 0, 2, 0, 6, 0, 0, 2, 0, 2, 0, 0, 0, 6, 0, 0, 0, 0, 2, 0, 0, 0, 6, 0, and 0, 0, 0, 2.